Section. Introduction. In recent years, we've seen a significant improvement in the capabilities of smaller, open large language models, LLMs. These models have evolved from the early GPT-2-like models to more accurate and compact versions. These newer models are trained on a much larger number of tokens than what was previously considered optimal according to the Chinchilla scaling laws. Researchers have found that these models can be further improved through a process called distilled supervised fine-tuning, DSFT. This involves using the output of a more advanced model, known as the teacher model, to guide the training of the student model. This method has been successful in enhancing the performance of open models across various tasks. However, it's important to note that these models still don't match the performance of the teacher models. One issue that users have pointed out is that these models are not intent-aligned. This means that they don't always behave in a way that aligns with the preferences of human users. This often results in outputs that don't provide the correct responses to queries. Measuring intention alignment has been challenging, but recent developments have led to the creation of benchmarks like MT-Bench and Alpaca Eval that specifically target this behavior. These benchmarks provide scores that closely correlate with human ratings of model outputs. They confirm that proprietary models perform better than open models trained with human feedback, which in turn perform better than open models trained with distillation. This highlights the importance of carefully collecting human feedback for alignment, even though it can be costly at scale. In our work, we focus on aligning a small open LLM entirely through distillation. We use AI feedback, AIF, from a group of teacher models as preference data and apply distilled direct preference optimization as the learning objective. This approach, which we refer to as dDPO, doesn't require any human annotation or sampling. By using a small base language model, we can train the resulting chat model in just a few hours. To validate this approach, we created Zephyr-7b, an aligned version of Mistral 7b. We first used DSFT, based on the Ultra Chat dataset. Then we used the AI feedback data collected in the Ultra Feedback dataset. Finally, we applied dDPO based on this feedback data. Our experiments show that this 7b parameter model can achieve performance comparable to 70b parameter chat models aligned with human feedback. However, it's important to note that our primary concern is with intent alignment of models for helpfulness. We haven't considered safety considerations of the models, such as whether they produce harmful outputs or provide illegal advice. This is technically more challenging to do because of added challenges in curating that type of synthetic data, and is an important subject for future work. There has been significant growth in the number of open large language models, LLMs, that have served as artifacts for the research community to study and use as a starting model for building chatbots and other applications. After the release of ChatGPT, the Llama model opened the doors to a wide range of research on efficient fine-tuning, longer pro-context, retrieval augmented generation, RAG, and quantization. With the development of open models, researchers have worked on approaches to improve small model performance by distillation from larger models. This trend started with self-instruct method and the Alpaca model, which was followed by Vicuña and other distilled models. These works primarily focused on distilling the SFT stage of alignment, whereas we focus on both SFT and preference optimization. Tools for benchmarking and evaluating LLMs have greatly evolved to keep up with the pace of innovation in generative AI. Powerful LLMs such as GPT-4 and Claude are used as evaluators to judge model responses by scoring model outputs or ranking responses in a pairwise setting. The LMSYS chatbot arena benchmarks LLMs in anonymous, randomized battles using crowdsourcing. The models are ranked based on their ELO ratings on the leaderboard. Alpaca Eval is an example of another such leaderboard that compares models in a pairwise setting but instead uses bigger LLMs such as GPT-4 and Claude in place of humans. In a similar spirit, MT-Bench uses GPT-4 to score model responses on a scale of 1 to 10 for multi-turn instructions across task categories such as reasoning, roleplay, math, coding, writing, humanities, STEM and extraction. The Hugging Face Open LLM Leaderboard, the Chain of Thought Hub, Chat Eval, and Fast Eval are examples of other tools for evaluating chatty models. We present results by evaluating on MT-Bench, Alpaca Eval, and the Hugging Face Open LLM Leaderboard. Section Summary. In recent years, smaller open large language models, LLMs, have improved significantly in their ability, surpassing the performance of compute-optimal models. Distilled supervised fine-tuning, DSFT, has been used to further train these models by leveraging a more capable teacher model. However, these models often lack intent alignment and do not behave in a manner that aligns with human preferences. To address this, a new approach called Distilled Direct Preference Optimization, dDPO, is proposed, which utilizes AI feedback from an ensemble of teacher models as preference data. This approach achieves comparable performance to models aligned with human feedback, without the need for human annotation or sampling. Section. Method. In this study, we aim to align a freely available large language model to the user's intent. We assume that we have access to a larger, more advanced model, which we refer to as the teacher model. Our objective is to create a student model that follows similar stages as the Instruct GPT model, as shown in the figure. We start with a raw large language model and train it to respond to user prompts. This is typically done through supervised fine-tuning on a dataset of high-quality instructions and responses. However, given access to a teacher model, we can have the model generate instructions and responses, and train the model directly on these. We call this method Distilled Supervised Fine-Tuning, or DSFT. To implement DSFT, we follow the self-instruct protocol. We start with a set of seed prompts that represent a diverse range of topics. We then construct a dataset through iterative self-prompting, where the teacher model is used to respond to an instruction and refine the instruction based on the response. The final dataset consists of pairs of instructions and responses. In our experiments, we use the Mistral 7B model, which is currently the best base language model at the 7B parameter scale. We use the Transformer Reinforcement Learning Library for fine-tuning, along with DeepSpeed 03 and FLASHATTENTION2 to optimize memory and improve training speed. All models are trained with the AtomW optimizer and no weight decay. We didn't experiment with parameter-efficient techniques such as LoRa, but we expect similar results with these methods. All experiments were run on 16A100S using bfloat 16 precision and typically took 2 to 4 hours to complete. We focus on 2 dialogue datasets that have been distilled from a mix of open and proprietary models. The first, UltraChat, is a self-refinement dataset consisting of 1.47 million multi-turn dialogues generated by GPT-3.5-TURBO over 30 topics and 20 different types of text material. The second, UltraFeedback, consists of 64,000 prompts, each of which have 4 large language model responses that are rated by GPT-4 according to criteria like instruction following, honesty, and helpfulness. Our main evaluations are on single-turn and multi-turn chat benchmarks that measure a model's ability to follow instructions and respond to challenging prompts across a diverse range of domains. We also evaluate our model on the Open LLM Leaderboard, which measures the performance of language models across 4 multi-class classification tasks. Across all benchmarks, we compare our model against a variety of open and proprietary models, each with different alignment procedures. Section Summary. The goal of this work is to align a large language model to user intent by training it to respond to user prompts. They propose a method called Distilled Supervised Fine-Tuning, DSFT, where a teacher model generates instructions and responses, which are then used to train the student model. They evaluate their approach on various benchmarks and compare it to other models with different alignment procedures. Section. Details of SFT training. We'll now explain the training process for our SFT and dPO models. We train these models for 1 to 3 cycles. For the SFT models, we use a cosine learning rate scheduler with a peak learning rate of 0.00002 and 10% warm-up steps. We train all models with a batch size of 512 and use packing with a sequence length of 2048 tokens. For the dPO models, we use a linear learning rate scheduler with a peak learning rate of 0.0000005 and 10% warm-up steps. We train all models with a batch size of 32 and use a beta value of 0.1 to control the deviation from the reference model. Our final Zephyr 7B model was initialized from the SFT model that was trained for 1 cycle and further optimized for 3 dPO cycles. Now, let's discuss the results. Our Zephyr 7B model outperforms other Open 7B models on the MT bench and Alpaca eval benchmarks, setting a new standard. It performs significantly better than DSFT models across both benchmarks. It also outperforms XWINLM7B, which is one of the few open models to be trained with distilled PPO, dPPO. When compared to larger open models, Zephyr 7B holds its own against LLAMA2CHAT70B, scoring better on MT bench and within 2 standard deviations on Alpaca eval. However, it doesn't perform as well as WIZARDLM70B and XWINLM70B, suggesting that applying dDPO to larger model sizes may be needed to match performance at these scales. When compared to proprietary models, Zephyr 7B is competitive with GPT-3.5-TU-RBO and Claude 2 on Alpaca eval. However, these results should be interpreted with caution as the pros in Alpaca eval may not be representative of real usage and advanced applications. We also found that Zephyr 7B is competitive with proprietary models on several categories, but it falls short in math and coding. Our dDPO model performs the best among all 7B models, with a significant gap over the best DSFT models as well as the XWIN-LM dPPO model. Larger models perform better than Zephyr on some of the knowledge-intensive tasks. However, Zephyr does reach the performance of the 40B scale models. We also examined the impact from different steps of the alignment process by fine-tuning Mistral 7B in 4 different ways. We found that without an initial SFT step, models are not able to learn at all from feedback and perform terribly. Using DSFT improves model score significantly on both chat benchmarks. We also considered running DSFT directly on the feedback data by training on the most preferred output. However, we found that this does not make an impact in performance. Finally, we see that the full Zephyr models, dDPO plus dDSFT, gives a large increase in both benchmarks. During the training of ZEPHYR7B, we observed that after 1 cycle of DPO training, the model would strongly overfit, as indicated by perfect training set accuracies. Surprisingly, this did not harm downstream performance on MT bench and Alpaca eval. However, we do observe that if the SFT model is trained for more than 1 cycle, the DPO step actually induces a performance regression with longer training.